Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. What intelligent alien technology might reveal? The search for extraterrestrial intelligence has focused primarily on listening for radio signals, deliberate transmissions from alien civilizations trying to communicate across the cosmos. Since 1960, when astronomer Frank Drake conducted the first systematic search for alien radio signals in what came to be called Project Ozma, scientists have scanned the sky with increasingly sensitive radio telescopes, hoping to detect patterns in the cosmic static that would indicate intelligent origin. But radio signals represent just one possible technological signature among countless ways that advanced civilizations might make their presence known across interstellar distances. Understanding what intelligent alien technology might reveal means thinking beyond communication attempts to consider the inevitable side effects and engineering projects that any sufficiently advanced civilization would produce. Technology leaves traces. Human civilization has only been producing radio signals for about a century. Yet already, our technological fingerprint extends outward in a sphere over 200 light-years in diameter, expanding at the speed of light. Television broadcasts, radar installations, radio communications, all of this electromagnetic radiation leaks into space, creating a bubble of human-generated signals spreading through the galaxy. An alien civilization with sensitive enough radio telescopes could detect these signals and know that an industrial, technological species exists on Earth, even if we never intentionally try to contact them. Our technology reveals us whether we choose to advertise our presence or not. The same principle applies to alien civilizations. Any technological species using electromagnetic radiation for communication, navigation, or industrial processes would inadvertently create detectable signals. The frequency, pattern, and characteristics of these signals would differ from natural astronomical sources. Natural radio emissions from stars, nebulae, and other cosmic objects tend to be broadband, spread across a wide range of frequencies, or if narrowband, they're produced by specific atomic or molecular transitions at predictable frequencies. Artificial signals, in contrast, might be extremely narrowband, might drift in frequency in patterns that reflect the relative motion of transmitter and receiver, or might contain modulations and patterns that have no natural explanation. The famous WOW signal detected in 1977 by the Big Ear radio telescope at Ohio State University demonstrated what a potential technosignature might look like. For 72 seconds, the telescope received a strong, narrow band signal from the direction of the constellation Sagittarius. The signal was so unusual that astronomer Jerry Amon wrote "Wow" on the printout, giving the detection its name. The signal has never been detected again, despite decades of subsequent observations, and its origin remains unexplained. It might have been terrestrial interference, or a reflection off space debris, or a natural phenomenon we don't yet understand, or it might have been exactly what it appeared to be, a brief, powerful transmission from an alien source that was never repeated. Optical signals represent another detection method. Laser technology on Earth has advanced to the point where powerful lasers could, in principle, outshine the sun at specific wavelengths for brief moments. If we pointed a sufficiently powerful laser at a star, an alien astronomer observing from that star system might detect the flash, recognizing it as artificial because of its extreme brightness at a single wavelength. This is the basis for optical SETI, the search for brief, intense laser pulses from other civilizations. Aliens might use lasers for interstellar communication because lasers are highly directional and can carry large amounts of information. A civilization intentionally trying to contact other species might beam powerful laser pulses toward nearby stars, hoping someone is watching. But some of the most compelling technosignatures might come not from communication attempts, but from large-scale engineering projects. Any advanced civilization would need energy, and energy requirements grow as civilizations become more technologically sophisticated. In 1964, physicist Freeman Dyson proposed that a sufficiently advanced civilization might construct a vast structure around its star to capture a significant fraction of the star's total energy output. This structure, called a Dyson sphere or Dyson swarm, might consist of countless solar panels, habitats, or other components orbiting the star, intercepting sunlight and converting it to useful energy. A complete Dyson sphere would make the star invisible at visible wavelengths. All the light would be absorbed by the structure, but the structure would glow in infrared radiation, emitting the waste heat from whatever processes the captured energy powered. From a distance, a star surrounded by a Dyson sphere would appear anomalously bright in infrared while being dim or invisible in visible light. Astronomers have searched for such infrared excess stars, cataloguing objects that might be Dyson spheres. Though all candidates discovered so far have more mundane explanations like dust clouds or unusual stellar properties. Megastructures don't need to enclose entire stars to be detectable. A single, enormous structure in orbit around a star might block a tiny fraction of the star's light as it passes in front of the star from our perspective. This would create a transit, a dip in the star's brightness, similar to what happens when a planet transits its star. But while planetary transits follow regular, predictable patterns with consistent depths and durations, a megastructure might create irregular, asymmetric transits that don't match any natural explanation. The star KIC 84462852, also known as Tabby's star after astronomer Tabitha Boyajian, who led the research team that discovered its unusual behavior, demonstrated what such anomalies might look like. This star, observed by the Kepler Space Telescope, exhibited irregular, dramatic dips in brightness, sometimes dropping by more than 20%, that didn't match the patterns expected from planets, dust clouds, or any other standard astronomical explanation. The irregular timing and unusual shapes of the dimming events led some researchers to speculate about megastructures, though most scientists now favour natural explanations involving dust and debris, possibly from a disintegrating comet or planet. Still, Tabby's star showed that we could detect anomalous dimming patterns, and if megastructures exist, similar observations might reveal them. Atmospheric pollution represents a more subtle, but potentially detectable, technosignature. Industrial civilizations inevitably alter their planet's atmosphere through their activities. On Earth, the Industrial Revolution increased carbon dioxide levels, added artificial chemicals like chlorofluorocarbons, and changed atmospheric chemistry in detectable ways. Some proposed technosignatures involve looking for molecules in exoplanet atmospheres that shouldn't exist naturally. Chlorofluorocarbons, for instance, are entirely artificial. They don't form through natural processes, but are produced industrially. Detecting CFCs in an exoplanet's atmosphere would be strong evidence for industrial activity. Similarly, nitrogen dioxide concentrations above natural levels could indicate industrial combustion. Certain combinations of atmospheric gases might indicate technological activity. For example, large amounts of both oxygen and methane in the same atmosphere shouldn't coexist naturally because these gases react with each other. If both are abundant, something must be continuously producing them. While biology can produce both gases, Certain ratios or the presence of specific isotopes might point toward industrial rather than biological sources. City lights offer another potential technosignature. Earth's night side is dramatically brighter than it was before artificial lighting, with cities visible from space as brilliant concentrations of light. An alien civilization observing Earth with sufficiently powerful telescopes could detect this artificial illumination, recognizing it as technological in origin because the light spectrum differs from natural phenomena, like forest fires or volcanic activity. The light would also be concentrated in specific patterns, along coastlines, in networks of roads, around population centers, rather than being randomly distributed. Detecting city lights on exoplanets would be extraordinarily challenging with current technology. The light from the planet's star overwhelms the faint glow of artificial lighting by enormous margins. But future telescopes, particularly those designed to directly image exoplanets by blocking the star's light, might have the sensitivity to detect bright illumination on a planet's night side, especially if the civilization uses inefficient lighting that wastes energy as light escaping into space, rather than being directed downward toward the ground. Space-based infrastructure might be detectable through reflected light or occultations. Satellites, space stations, solar panel arrays, and other orbital structures reflect light from their star. A civilization with extensive orbital infrastructure might create a faint cloud of reflected light around their planet, detectable as excess brightness beyond what the planet itself would reflect. Similarly, large orbital structures might occasionally pass in front of stars in the background as seen from Earth, creating very brief, tiny dips in brightness that could be detected through careful monitoring. Propulsion systems represent another potential technosignature. Any civilization attempting interstellar travel would need enormous energy to accelerate spacecraft to significant fractions of light speed. Some proposed propulsion systems would create detectable signatures. Nuclear pulse propulsion, using nuclear explosions for thrust, as proposed in the Orion project, would create distinctive radiation signatures. Antimatter engines would produce gamma rays from matter-antimatter annihilation. Fusion drives would create specific spectral signatures from the fusion reactions. Even laser-pushed light sails, sails accelerated by powerful lasers from the home star system, would create bright laser beams visible across interstellar distances to anyone positioned along the beam's path. Gravitational engineering, if possible, might create detectable anomalies. If advanced civilizations can manipulate gravity or space-time, something beyond our current technological capabilities, but not necessarily forbidden by physics, their activities might create detectable effects. Artificial gravitational waves at unusual frequencies, anomalous motions of stars or planets that suggest artificial manipulation, or regions of space with unexplained gravitational properties could all potentially indicate advanced technology at work. Asteroid mining and large-scale resource extraction would alter the appearance of solar systems. A civilization mining asteroids for raw materials would change the distribution and size of asteroids over time. Spectroscopic observations might reveal unusual compositions in asteroid belts, perhaps unusually low concentrations of useful metals if those metals have been extensively mined. Debris from mining operations might create distinctive dust clouds with unusual properties. Stellar engineering represents the extreme end of technological signatures. Some theorists have proposed that advanced civilizations might manipulate stars themselves, extracting material from stars, changing stellar composition, or even moving stars through space using enormous thrusters. These Shkadov thrusters, named after physicist Leonid Shkadov, would use mirrors or other structures to create thrust from a star's own radiation pressure, allowing the star to be slowly moved over millions of years. A civilization might move their star to escape dangers like nearby supernovae, to position their star system optimally in the galaxy, or to transport their entire solar system on an interstellar journey. A moving star whose motion couldn't be explained by gravitational interactions with other objects might indicate such stellar engineering. Time also factors into detectability. A civilization's technological signatures change as technology evolves. Humanity's radio era might be brief, perhaps only a few centuries between when we developed radio technology and when we transitioned to communication methods that don't leak into space, like fiber optics or directed transmissions. An alien civilization might have a similarly brief radio-loud period. This means that civilizations at different technological stages would produce different signatures. An early industrial civilization might produce atmospheric pollution, but no radio signals. A spacefaring civilization might have extensive orbital infrastructure, but might no longer use radio for communication. An extremely advanced civilization might produce signatures we cannot yet imagine, using technologies and engineering approaches completely beyond our current conceptual framework. The absence of detected technosignatures, despite decades of searching, has led to discussions of the Fermi paradox. If technological civilizations are common, where are their signatures? Perhaps they're too rare or too distant. Perhaps they exist but avoid broadcasting or producing detectable signatures intentionally. Perhaps our detection methods are inadequate or focused on the wrong signatures. Or perhaps advanced civilizations develop technologies that produce no detectable signatures, or signatures we wouldn't recognize because we're not looking for them. What intelligent alien technology might reveal encompasses everything from deliberate messages transmitted across space to the inevitable waste heat and pollution from industrial processes, from the dimming of stars caused by megastructures to the reflected light from orbital infrastructure, from laser flashes used for communication to the gravitational anomalies created by stellar engineering. Each technological signature represents a different window into how civilizations develop, what they value, what problems they solve, and how they reshape their environments. Detecting any of these signatures would answer one of humanity's deepest questions: are we alone? And would provide our first glimpse into how other intelligences have developed technology, overcome challenges, and left their mark on the cosmos, transforming our understanding of what's possible, and revealing that the universe contains not just stars, planets, and lifeless matter, but minds that contemplate the cosmos just as we do, minds that build and create and reach toward the stars. What alien oceans might contain? Earth's oceans are vast, salty bodies of liquid water covering more than 70% of the planet's surface, containing dissolved minerals, organic molecules, and a staggering diversity of life, from microscopic bacteria to the largest animals that have ever existed. But oceans on other worlds might be fundamentally different, not just in what organisms inhabit them, but in their very composition, what liquids fill them, what chemicals dissolve in those liquids, and what physical conditions prevail at their depths. Understanding what alien oceans might contain means considering not only water-based oceans with different chemistry than Earth's seas, but entirely different liquids that could serve as oceanic solvents on worlds with radically different temperatures, pressures, and geological histories. The most familiar alien oceans would be water-based oceans on other worlds. Several candidates exist in our own solar system. Europa, Jupiter's ice-covered moon, harbours a global ocean containing perhaps twice as much liquid water as all of Earth's oceans combined, kept liquid by tidal heating from Jupiter's gravity despite surface temperatures around -160 degrees Celsius. This ocean lies beneath an ice shell estimated to be 15 to 25 kilometers thick, shielding the water from the vacuum of space and from Jupiter's intense radiation belts. What Europa's ocean contains remains unknown, but scientific models and the limited data from spacecraft flybys provide clues. The ocean is certainly salty, likely containing dissolved salts leached from Europa's rocky seafloor over billions of years. Magnesium sulfate, sodium chloride, and other salts detected spectroscopically in Europa's ice shell probably came from the ocean below. The salinity might be similar to Earth's oceans, or it might be substantially higher, creating a briny sea where salt concentrations affect water's freezing point, density, and chemistry. High salinity would influence what kinds of life could potentially evolve, favouring organisms with mechanisms to cope with osmotic stress. The ocean would be dark. Absolutely no sunlight penetrates through kilometres of ice. Any life in Europa's ocean would depend on chemical energy rather than photosynthesis. The rocky seafloor might host hydrothermal vents similar to those on Earth's ocean floor, where hot, mineral-rich water spews from cracks in the rock, driven by volcanic heat from the moon's interior. These vents could provide energy and nutrients to support chemosynthetic bacteria that extract energy from chemicals in the vent fluids: hydrogen, methane, hydrogen sulfide, iron compounds. If such microbes exist, they might form the base of a food chain, supporting more complex organisms analogous to the tube worms, clams, and crustaceans that cluster around Earth's hydrothermal vents. Dissolved gases would be present in Europa's ocean: carbon dioxide from reactions between water and rock, hydrogen from water-rock reactions, and possibly from radiolysis, where radiation breaks apart water molecules near the ice-ocean boundary, methane from geological processes, or potentially from biological activity. The concentrations and ratios of these gases would reveal much about the ocean's chemistry and whether biological processes might be occurring. Organic molecules, carbon-based compounds, almost certainly exist in Europa's ocean. Comets and meteorites containing organic compounds have bombarded Europa throughout its history. Chemical reactions between water and rock produce simple organic molecules. If life exists, it would produce far more complex organic molecules: amino acids, lipids, sugars, proteins. Detecting complex organic molecules in samples from Europa's ocean would be strong evidence for biology, though distinguishing biological from non-biological organic chemistry would require careful analysis. Enceladus, Saturn's small moon, provides an even more accessible alien ocean because it actively vents ocean water into space through cracks in its south polar ice shell. The Cassini spacecraft flew through these plumes, analysing their composition directly. The plumes contain water vapour, ice grains, carbon dioxide, methane, ammonia, molecular hydrogen, and complex organic molecules, including some with chains of carbon atoms, ingredients that on Earth would suggest habitability. The presence of molecular hydrogen is particularly intriguing because it suggests water-rock reactions at high temperatures, consistent with hydrothermal vents on Enceladus's seafloor. The organic molecules, while not proof of life, show that organic chemistry is occurring in Enceladus's ocean. Titan, Saturn's largest moon, presents an entirely different type of ocean, not water, but liquid hydrocarbons. Titan's surface temperature hovers around -180 degrees Celsius, far too cold for liquid water, which is frozen as hard as rock. But at these temperatures, methane and ethane exist as liquids. Titan has lakes and seas of liquid hydrocarbons near its poles, bodies of liquid methane and ethane with dissolved propane, butane, nitrogen, and traces of more complex organic molecules. These hydrocarbon seas are hundreds of meters deep in some places, creating environments completely unlike anything on Earth. What Titan's hydrocarbon oceans might contain depends on what chemistry can occur in liquid methane at cryogenic temperatures. Organic chemistry certainly happens. Titan's atmosphere produces complex organic molecules through photochemistry, and these molecules rain down onto the surface, accumulating in the lakes and seas. Nitrogen compounds, cyclic molecules, long-chain hydrocarbons, and possibly even more complex molecules might dissolve in the methane. Whether life could exist in liquid methane remains highly speculative, but if it does, it would use completely different biochemistry than Earth life, perhaps with cell membranes made from molecules that are insoluble in hydrocarbons rather than the water-soluble membranes Earth organisms use. Titan also likely has a subsurface water ocean beneath its icy crust, similar to Europa and Enceladus. This buried ocean would be separate from the surface hydrocarbon seas, creating the possibility that Titan might host two completely different types of chemistry: water-based chemistry in the deep subsurface ocean and hydrocarbon-based chemistry in the surface seas. Whether these two environments could both support life, and whether life in one could be related to life in the other, represents one of the most intriguing questions about this remarkable moon. Ammonia oceans represent another possibility for alien seas. Ammonia remains liquid at temperatures between -77 and -33 degrees Celsius at Earth atmospheric pressure, colder than water but warmer than methane. A planet or moon with temperatures in this range might have oceans of liquid ammonia or ammonia-water mixtures. Pure ammonia is a less effective solvent than water for many compounds, but it can dissolve different substances than water, creating entirely different ocean chemistry. An ammonia ocean would be less dense than water ice, so ammonia ice would sink rather than float, potentially affecting planetary heat transport and ocean circulation. The ocean's pH would be highly alkaline. Ammonia is a base, creating chemistry very different from Earth's near-neutral oceans. Organisms adapted to ammonia oceans would need biochemistry that functions at low temperatures and high pH, potentially using ammonia molecules in ways analogous to how Earth life uses water. Sulfuric acid oceans sound implausible, yet Venus's clouds contain concentrated sulfuric acid droplets, and some scientists have speculated about life existing in these droplets. While Venus's surface is hellishly hot, the cloud layers at altitudes of 50 to 60 kilometers above the surface have temperatures around room temperature, quite comfortable by terrestrial standards. If life could exist as airborne organisms living in cloud droplets, those droplets would be concentrated sulfuric acid, requiring biochemistry completely unlike anything on Earth. Certain Earth microbes can tolerate extremely acidic conditions, proving that acid-resistant biochemistry is possible. But whether life could actually live in sulfuric acid remains unknown and highly controversial. Silicate oceans, molten rock, might exist on lava worlds orbiting extremely close to their stars. At temperatures exceeding 2000 degrees Celsius, rock melts into liquid magma that flows like water. While most scientists consider molten rock too hot and destructive for any conceivable biochemistry, some speculative theories propose exotic life forms based on completely different chemistry that might exist in magma, perhaps using silicate molecules or metal compounds as structural materials instead of carbon-based organic molecules. Such life would be so alien that we might not recognize it as life, even if we observed it directly. Supercritical oceans exist under conditions where temperature and pressure are high enough that the distinction between liquid and gas breaks down. Supercritical water, existing at temperatures above 374 degrees Celsius and pressures above 220 atmospheres, has properties intermediate between liquid and gas. Deep beneath the surfaces of massive ocean worlds, pressures might be high enough to create supercritical water oceans. The chemistry in supercritical water differs dramatically from normal water chemistry, with different solubilities, reaction rates, and molecular interactions. Whether life could adapt to supercritical conditions remains unknown, but the possibility can't be ruled out for extremely exotic organisms. The ocean floor composition profoundly affects ocean chemistry. Earth's ocean floors are basaltic rock, and water-rock interactions continuously cycle elements between the ocean and the crust. Alien ocean floors might be different, perhaps pure ice if the ocean is deep enough that high-pressure ice forms at the bottom, or perhaps carbonate rocks, serpentinite, or other minerals depending on the planet's composition. These different minerals would leach different elements into the ocean, creating different dissolved chemistry. Hydrothermal vents on alien seafloors might vent fluids with very different composition than Earth's vents. On Europa or Enceladus, where the rocky interiors might be rich in different minerals than Earth's mantle, vent fluids might contain unusual concentrations of metals, sulfur compounds, or other chemicals. These different chemistries would favor different types of chemosynthetic organisms if life exists, potentially creating ecosystems with no analogue on Earth. Dissolved oxygen would be rare or absent in most alien oceans unless photosynthetic life has evolved and produced oxygen for billions of years as on Earth. Most alien oceans would be anoxic, without dissolved oxygen, more similar to Earth's oceans before the Great Oxidation Event 2.5 billion years ago. Anoxic oceans contain different dissolved metals and have different chemistry than oxygenated oceans. Iron remains dissolved in anoxic water instead of precipitating as rust. Sulfur chemistry dominates, rather than oxygen chemistry. Life in anoxic alien oceans would use anaerobic metabolism, extracting energy from reactions that don't involve oxygen. Temperature gradients in alien oceans depend on heat sources. Earth's oceans are heated from above by sunlight and from below by geothermal heat, creating complex circulation patterns. Europa's ocean, heated only from below by tidal heating and with a cold ice ceiling above, might have upside-down circulation compared to Earth. Warm water rising from the seafloor toward the ice ceiling where it cools and sinks back down. These circulation patterns would affect nutrient distribution, temperature zones, and where life might be most abundant. Pressure increases with depth in any ocean, but the rate depends on the liquid's density and the world's gravity. Europa's ocean might reach pressures exceeding 10,000 atmospheres at the seafloor, much higher than Earth's deepest ocean trenches, due to the ocean's great depth. Organisms adapted to such extreme pressure would have specialized biochemistry that functions under conditions where molecules are compressed and reaction rates are altered by pressure's effects on molecular structure. Seasonal variations might affect some alien oceans. A planet with significant axial tilt would experience seasonal changes in star heating that could affect surface ocean temperatures, causing seasonal mixing, ice formation and melting, and biological cycles tied to seasons. Tidally locked planets would have no seasonal variations, but might have temperature zones related to distance from the substellar point, the location where the star is directly overhead, creating warm equatorial regions and cold polar regions with different ocean chemistry in each zone. Ice-covered oceans might have ecosystems concentrated near the ice-water boundary, where any photosynthesis using radiation penetrating through cracks in the ice could occur, or where chemical gradients between the ice and deep ocean creates energy harvesting opportunities. Life might cluster in cracks and crevices in the ice ceiling, or in regions where the ice is thinnest and most likely to crack or melt. What alien oceans might contain ranges from the familiar, salty water with dissolved minerals and potentially abundant life, to the exotic, liquid methane seas with dissolved organic compounds, ammonia oceans at cryogenic temperatures, supercritical fluids blurring the line between liquid and gas, even molten silicate magmas on scorching hot worlds. Each ocean's composition reflects its world's temperature, pressure, geology, and history, creating environments where chemistry operates under different rules, where life, if it exists, would be adapted to conditions we can barely imagine, where exploration by future spacecraft might reveal ecosystems as diverse and wondrous as Earth's oceans are so alien that we struggle to recognize biology when we see it, expanding the inventory of habitable environments to include not just Earth-like water oceans, but any stable liquid where dissolved chemicals, energy sources, and sufficient time might allow chemistry to evolve into biology beneath the waves of alien seas scattered across the solar system and beyond. The universal laws that would shape all life. While alien life might look nothing like Earth's organisms, using different chemistry, different genetic molecules, different metabolic pathways, certain fundamental principles would constrain and shape all life everywhere in the universe. These universal laws arise not from biological specifics, but from physics, chemistry, thermodynamics, and information theory, disciplines that operate identically throughout the cosmos. Understanding these universal constraints reveals what all life, no matter how alien, must have in common, and what fundamental challenges every living system must solve to exist, grow, reproduce, and evolve on any world under any star in any galaxy. The laws of thermodynamics govern all physical processes, and life is no exception. The second law of thermodynamics states that entropy, disorder, tends to increase in closed systems. Left to themselves, organized structures break down, concentrated energy disperses, and order gives way to chaos. A sandcastle erodes, a hot cup of coffee cools to room temperature. Complex molecules break apart into simpler ones. This universal tendency toward disorder creates life's fundamental challenge. Living organisms are highly organized, low-entropy systems existing in a universe that constantly pushes toward disorder. Maintaining biological organization requires constant energy input to fight against entropy's relentless pull. All life, everywhere in the universe, must extract energy from its environment and use that energy to maintain and build ordered structures. On Earth, photosynthetic organisms capture energy from sunlight. Other organisms obtain energy by consuming and metabolizing food, breaking down the chemical bonds in organic molecules and harnessing the released energy. Chemosynthetic organisms extract energy from inorganic chemical reactions. The specific mechanisms vary enormously, but the underlying requirement is universal. Every living thing must have a metabolism, some way of extracting usable energy from its surroundings to power the processes that maintain life. This creates a fundamental constraint. Life can only exist where energy flows. Environments in perfect thermodynamic equilibrium, where no energy gradients exist, cannot support life. Life requires disequilibrium, a hot vent and cold water, sunlight falling on chemical systems, redox gradients between different chemical species. These disequilibria provide the energy flow that life harnesses. Alien life, no matter what chemistry it uses or what planet it inhabits, must exist in regions where energy flows from higher to lower energy states, capturing some of that flowing energy to power metabolism. Evolution through natural selection represents another universal principle. Any system capable of reproduction, variation, and selection will inevitably evolve. This is not a biological principle, but a logical and mathematical necessity. If organisms reproduce, creating copies of themselves, and if those copies are not perfect but contain variations, and if some variants survive and reproduce more successfully than others due to those variations, then the population will change over generations as successful variants become more common and unsuccessful variants decline. This is evolution by natural selection, and it operates on any replicating system with heritable variation subject to selection pressures. Alien life would therefore inevitably evolve, becoming adapted to its environment through countless generations of selection favouring organisms better suited to local conditions. The specific adaptations would differ. Alien organisms might evolve features we've never imagined, but the process would be the same. Evolution is not optional or unique to Earth. It's a fundamental consequence of how replicating systems behave over time. Any civilization that discovers alien life would find that life has been shaped by evolution just as Earth's life has been shaped, even if the resulting organisms look and function completely differently. This evolutionary principle creates a corollary, convergent evolution, where different lineages independently evolve similar solutions to similar problems, occurs because physics and chemistry constrain the possible solutions. Eyes evolved independently many times on Earth because detecting light provides such valuable information, and focusing light onto photosensitive cells is the most effective way to create detailed images. Streamlined body shapes evolved independently in fish, dolphins, ichthyosaurs, and penguins because that shape minimizes drag in water. These convergences occur because physical laws determine what works well in given circumstances. Alien life would show similar convergences. Any organism that needs to move through fluid efficiently would likely evolve some form of streamlined shape because physics demands it. Any organism that needs to detect electromagnetic radiation would likely evolve some structure that captures and focuses that radiation. The details would vary. Alien eyes might have 10 light-sensing structures instead of 2, might sense infrared instead of visible light, might use completely different photosensitive molecules than Earth organisms. But the basic function would be similar because the physics of light detection operates universally. Information storage and transmission represent another universal requirement. Living organisms must store information about how to build and maintain themselves, and they must transmit this information to their offspring. On Earth, this information is stored in DNA and RNA sequences, but the specific molecule doesn't matter. What matters is that some physical system must encode instructions that can be copied and passed to the next generation, and these instructions must contain enough information to specify the organism's structure and function with sufficient detail that offspring resemble parents. The amount of information required sets minimum limits on the complexity of genetic systems. A viable organism cannot be specified by just a few bits of information. It requires substantial information content to encode even the simplest metabolic pathways, structural components, and reproduction mechanisms. Earth's simplest free-living bacteria have genomes containing roughly 500,000 base pairs, encoding about 500 genes. This represents the approximate minimum information content for independent life under Earth conditions. Alien life might require more or less information, depending on environmental complexity and metabolic strategies, but some minimum threshold exists below which organisms cannot encode enough instructions to function and reproduce reliably. The fidelity of information copying, how accurately genetic information is replicated, creates a universal trade-off. Perfect copying with zero errors would prevent evolution because no variation would arise. But too many copying errors would lead to error catastrophe, where genetic information degrades faster than selection can eliminate harmful mutations. There exists an optimal error rate that balances stability and evolvability, allowing organisms to maintain essential functions while still generating the variation necessary for adaptation. Alien genetic systems would face this same trade-off and would likely evolve error rates in a similar optimal range, regardless of what molecules store their genetic information. Physical scaling laws constrain organism size and structure. The strength of materials scales with cross-sectional area proportional to the square of linear dimensions, while weight scales with volume proportional to the cube of linear dimensions. This means that as organisms get larger, their weight increases faster than their structural strength. A human scaled up to 10 times normal height would weigh 1,000 times as much, but would have bones only 100 times as strong. The skeleton would collapse under the weight. This scaling law explains why large land animals have thick, sturdy legs relative to their body size, while small animals have gracile limbs. Elephants have legs like pillars. Mice have delicate, thin legs. An alien planet with higher gravity would have organisms with even thicker, stronger structural supports relative to their size. A lower gravity planet would allow more slender structures. But the mathematics of scaling operates universally, constraining what body plans are physically possible at different sizes. Surface area to volume ratio creates another universal constraint. Small organisms have large surface area relative to their volume, making heat loss rapid and making diffusion effective for transporting materials. Large organisms have small surface area relative to volume, retaining heat more effectively but requiring specialized circulatory systems because diffusion becomes inadequate for transporting nutrients and waste across large distances. These scaling relationships would govern alien life just as they govern Earth life, determining which transport mechanisms are necessary at different sizes and what thermal regulation strategies are required. Chemical reaction rates depend on temperature, creating universal constraints on metabolism. Higher temperatures speed up chemical reactions exponentially. A rule of thumb is that reactions roughly double in rate for every 10-degree increase in temperature. This means organisms in hot environments can have faster metabolisms, grow more quickly, and potentially think faster if they're intelligent. Organisms in cold environments have slower metabolisms, grow more slowly, and would process information more slowly if conscious. These temperature effects on reaction kinetics are universal, affecting any chemistry-based life regardless of specific biochemistry. Diffusion rates determined by physics limit how large cells can be. Molecules move through cells by random thermal motion, diffusion. This process is slow. A molecule might take seconds or minutes to diffuse across a large cell. This limits cell size because cells need to move nutrients, wastes and signals around internally, and diffusion becomes prohibitively slow beyond certain sizes. Earth's largest cells are only about 1 millimeter across, and most are much smaller. Alien cells, regardless of their chemistry, would face similar diffusion limits unless they evolved active transport mechanisms, like Earth's eukaryotic cells use, with molecular motors moving cargo along cellular highways. The speed of light creates absolute limits on information transfer. No signal can travel faster than light, which means there are minimum response times for any organism based on its size. An organism the size of a bacterium, a few micrometers, experiences internal light travel times of trillionths of a second, essentially instantaneous. But a hypothetical, planet-sized organism would experience light travel times of tens of milliseconds from one side to the other, creating unavoidable delays in communication and coordination between distant parts. Very large organisms would necessarily be slow to respond to stimuli and might need decentralized control systems because centralized coordination becomes impractical when signal delays become significant. Energy efficiency sets ultimate limits on what metabolic processes are possible. Chemical reactions have maximum energy yields determined by the bonds being broken and formed. An organism cannot extract more energy from a reaction than the chemistry allows. This means life on worlds with limited energy availability, dim stars, deep subsurface environments, chemical poor conditions would necessarily have low energy lifestyles, growing slowly and reproducing infrequently. High energy environments allow active, energetic lifestyles, but also demand mechanisms to dissipate excess heat. Water's unique properties, while not absolutely required for life, make it an excellent solvent for biochemistry. Water remains liquid across a convenient temperature range, has high heat capacity that buffers against temperature changes, expands when freezing so ice floats, acts as a polar solvent that dissolves ions and many organic molecules, and participates in many biochemical reactions. While life could potentially use other solvents, liquid ammonia, methane, supercritical carbon dioxide, any solvent must have properties that allow complex chemistry to occur, molecules to dissolve and interact, and cellular compartments to form. Not many liquids have the right combination of properties, making water-based life probably more common than exotic alternatives, though not exclusively so. Complexity emerges hierarchically, with simple components combining into more complex structures, which combine into still more complex systems. Atoms form molecules. Molecules form macromolecules. Macromolecules form cellular structures. Cells form tissues. Tissues form organs. Organs form organisms. Organisms form ecosystems. This hierarchical organization seems to be how complexity arises universally, because building complex systems directly from simple components becomes unmanageable beyond certain complexity levels. Modular hierarchical construction allows greater complexity to be achieved and maintained. Alien life would likely show similar hierarchical organization, even if the specific components at each level differ completely from Earth's biological hierarchy. Darwinian selection favors efficiency. Organisms that use resources more efficiently have advantages over wasteful competitors. This drives evolution toward optimized solutions within physical constraints. Alien life would similarly be shaped by selection for efficiency, though what constitutes efficient depends on environmental context. In energy-rich environments, speed might matter more than efficiency. In energy-poor environments, extreme efficiency becomes essential for survival. But the general principle that natural selection tends to optimize organisms for their specific circumstances within physical constraints operates universally. The universal laws that would shape all life encompass thermodynamics, demanding that life exist only where energy flows, and that organisms extract energy to maintain order against entropy. Evolution, through natural selection, being an inevitable consequence of imperfect replication with variation. Information requirements, setting minimum complexity thresholds, scaling laws constraining size and structure, chemical kinetics determining metabolic rates, and physical limits on signal speeds, and diffusion rates imposing fundamental constraints on how large and fast organisms can be. These laws operate identically throughout the universe, guaranteeing that while alien life might look and function completely differently from Earth's organisms in countless details, the fundamental principles governing life's existence, evolution, and physical limitations would be the same everywhere, creating a common framework that all life must operate within, regardless of whether it's based on carbon or silicon, DNA or something entirely different, oxygen metabolism or sulfur chemistry. Because physics and chemistry and thermodynamics and information theory operate identically on every world orbiting every star in every galaxy, creating universal constraints that shape all possible forms of life into entities that must harvest energy, maintain organization, store and transmit information, and evolve through selection, making these principles the true universals of biology that would apply to any living thing humans might ever encounter. What comets are really made of? Comets have captivated human imagination for millennia, appearing in the sky as ghostly visitors with long tails that stretch across the heavens. Ancient civilizations often viewed them as omens or messengers from the gods. But these cosmic wanderers are not supernatural phenomena. They're physical objects composed of specific materials that reveal the history of the solar system's formation. Understanding what comets are made of means understanding some of the most pristine, unchanged matter left over from the birth of our planetary system billions of years ago. The core of every comet is its nucleus, a solid chunk of ice and rock that can range from a few hundred meters to tens of kilometers across. In 1950, astronomer Fred Whipple proposed what became known as the dirty snowball model of comets, suggesting that comet nuclei were mixtures of ice and dust. This model has proven remarkably accurate, though modern observations have revealed that comets might be better described as icy dirt balls. They contain more rock and dust than Whipple initially thought, sometimes with dust making up 50% or more of their mass. The ice in a comet is primarily water ice, frozen solid at the incredibly cold temperatures found in the outer solar system. But comets contain more than just frozen water. They also harbour other volatile compounds, substances that evaporate at relatively low temperatures. Carbon monoxide ice exists in comet nuclei, freezing at temperatures even lower than water. Carbon dioxide, frozen into dry ice, is abundant in many comets. Methane, ammonia, formaldehyde, methanol, and hydrogen cyanide have all been detected in comets, creating a chemical inventory that reads like an exotic mixture of the simplest molecules that carbon, nitrogen, and oxygen can form when combined with hydrogen. These volatile compounds exist as ices throughout the comet's interior when it's far from the Sun, creating a porous, fluffy structure rather like hard frozen snow. The density of comet nuclei is remarkably low, typically less than water, around 0.6 grams per cubic centimetre. This low density reveals that comets are not solid blocks of ice, but rather loosely consolidated collections of icy particles with substantial void space between them. Picture a pile of snowballs loosely stuck together rather than a single solid block of ice, and you have a reasonable mental image of a comet's internal structure. Mixed throughout this icy matrix are dust particles, tiny grains of rock and organic material. These dust grains are incredibly small, typically measured in micrometers, smaller than the width of a human hair. They're composed of silicates similar to the minerals found in Earth's rocks, compounds of silicon and oxygen mixed with elements like magnesium and iron. Some grains are pure carbon, forming soot-like particles. Others are complex mixtures of organic molecules, carbon-based compounds that include some of the building blocks of life. The organic material in comets is particularly fascinating. When spacecraft have analysed comets up close, or when laboratories have examined samples collected from comet tails, they've found complex organic molecules, including amino acids, the building blocks of proteins, and nucleobases, components of DNA and RNA. These molecules don't indicate that comets harbour life, but they demonstrate that the chemical precursors necessary for life can form naturally in space and were present in the early solar system. Some scientists have proposed that comets bombarding the early Earth might have delivered substantial quantities of organic molecules and water, potentially contributing to the origins of life on our planet. The European Space Agency's Rosetta mission, which orbited and studied Comet 67P/Churyumov-Gerasimenko from 2014 to 2016, provided unprecedented detail about comet composition. The Philae lander, which touched down on the comet's surface, detected 16 organic compounds as the comet's warmth released them from the ice. Among these were 4 compounds never before detected on a comet, including molecules that can act as precursors to amino acids. The comet's surface appeared darker than coal, with a reflectivity of only about 6%, due to the dark organic compounds mixed with the ice. When a comet approaches the Sun, solar heating begins to affect its structure. At distances beyond about 5 astronomical units, 5 times the Earth-Sun distance, roughly Jupiter's orbit, a comet remains frozen and inert. But as it moves closer, sunlight warms the surface. The most volatile ices, like carbon monoxide and carbon dioxide, begin to sublimate, transforming directly from solid to gas without passing through a liquid phase. This sublimation creates pressure beneath the surface, and when that pressure becomes strong enough, gas bursts through the surface, carrying dust particles along with it. These jets of gas and dust create the coma, the glowing atmosphere that surrounds the nucleus and makes the comet visible from Earth. The coma can grow to enormous sizes, sometimes exceeding the diameter of Jupiter, even though the nucleus producing it might be only a few kilometers across. The gas molecules in the coma, particularly water vapor, are broken apart by solar ultraviolet radiation, creating a complex chemistry. Hydroxyl radicals, hydrogen atoms, oxygen atoms, and other fragments fluoresce in sunlight, emitting light at specific wavelengths that give the coma its greenish or bluish tint. The dust released from the comet creates a dust tail, pushed away from the sun by radiation pressure, the physical push that photons exert when they strike and reflect off particles. This dust tail typically appears yellowish-white because it's sunlight reflecting off dust particles. The tail can extend for millions of miles, creating the spectacular displays visible from Earth. A separate ion tail, composed of ionized gas molecules, is pushed by the solar wind rather than radiation pressure. The ion tail glows with its own light as the ionized molecules fluoresce, often appearing blue due to emissions from ionized carbon monoxide. This ion tail points directly away from the sun, shaped by the magnetic fields carried in the solar wind. The nucleus itself undergoes changes as the comet repeatedly approaches the sun. Each passage evaporates a layer of ice from the surface, typically removing a few meters of material per orbit for comets that pass close to the sun. As the ice sublimates, some dust particles escape with the gas, but others fall back to the surface, gradually building up a layer of dust and larger rock fragments. Over many orbits, this can create a crust of non-volatile material covering the underlying ice, insulating it from solar heating. Some old comets develop such thick crusts that they become inactive, no longer producing visible comas or tails, even when they approach the sun. NASA's Deep Impact mission in 2005 deliberately crashed a copper impactor into Comet Tempel 1 to excavate beneath the surface and observe the fresh material. The impact created a crater and ejected plumes of material that spectroscopic analysis revealed to be rich in water ice mixed with organic compounds and fine dust. The material beneath the surface appeared similar to, but slightly richer in ice than the surface material, confirming that the interior retains more pristine composition while the surface becomes processed by solar heating. The ratio of different isotopes in comet materials provides clues about where and when they formed. Deuterium, a heavy isotope of hydrogen with an extra neutron, exists in different ratios to normal hydrogen depending on the temperature at which water formed. Measurements of the deuterium to hydrogen ratio in various comets have shown considerable variation, suggesting that comets formed in different regions of the early solar system or at different times. Some comets have deuterium ratios similar to Earth's oceans, while others differ substantially, helping scientists understand whether comets could have delivered Earth's water. The dust particles in comets are themselves diverse and complex. Some grains are crystalline, showing that they formed at high temperatures, possibly near the young sun, then were transported outward and incorporated into comets forming in the cold outer solar system. Other grains are amorphous, formed at low temperatures in the outer reaches. This mixture indicates that the solar nebula was not a static, orderly system, but rather a dynamic environment with extensive mixing, where materials formed in the hot inner regions could be transported outward, and vice versa. Comets also contain tiny pre-solar grains, particles that formed around other stars before the sun existed and survived incorporation into our solar system. These grains have isotopic compositions distinctly different from solar system materials, marking them as true interstellar visitors preserved within comets. They're typically only nanometers to micrometers in size, but they're extraordinarily valuable because they provide samples of stars that lived and died before our solar system formed, preserved in these frozen time capsules. When comets break apart, as they sometimes do when tidal forces or internal pressure cause the nucleus to fragment. The exposed interior shows the layered structure built up over billions of years. Some regions are richer in ice, others in dust. Some layers contain different mixtures of volatile compounds. These variations likely reflect changes in conditions in the solar nebula as the comet grew by accumulation, recording the changing composition of material in the comet-forming region over time. The darkening of comet surfaces producing the surprisingly low reflectivity observed by Rosetta and other missions results from the organic compounds being altered by solar radiation and cosmic rays. This radiation processing, called space weathering, gradually darkens and reddens the surface materials over time. The very dark surfaces of comet nuclei tell us they've been exposed to space for long periods, accumulating radiation damage that has transformed the original icy material into a darker, more complex mixture. Comets are messengers from the outer solar system, preserving materials that have remained largely unchanged for over 4 billion years. While planets have been geologically active, melting and reforming their materials countless times, and asteroids have been heated and altered, comets have remained frozen in the deep cold of the outer solar system, maintaining their original composition. They're samples of the primordial solar nebula, the disk of gas and dust from which the planets formed, carrying within their icy matrices the water, organic molecules, and mineral grains that were present at the dawn of the planetary system, offering glimpses into the raw materials from which everything in our solar system, including Earth and ultimately life itself, was constructed. What happens at the edge of a black hole? At the edge of a black hole lies one of the most extreme boundaries in the universe, a point of no return called the event horizon. This invisible surface marks the place where gravity becomes so overwhelmingly powerful that nothing, not even light itself, can escape. Cross this threshold, and you are severed from the rest of the universe forever, drawn inexorably toward the singularity at the center. Understanding what happens at this edge requires thinking about space and time in ways that challenge everything. Our everyday experience tells us about how reality works. Imagine approaching a black hole from a safe distance. At first, it wouldn't look like much, just a region of absolute darkness against the star-filled background of space. But as you drew closer, you would begin to notice something strange happening to the light around you. Stars behind the black hole would appear distorted, their light bent around the black hole's mass in graceful arcs. Some stars would appear in multiple locations simultaneously as their light took different curved paths around the black hole to reach your eyes. This gravitational lensing creates a visual effect like looking through a cosmic funhouse mirror, with the entire background of space warped and twisted around the dark sphere. The event horizon itself is defined by a specific radius from the center of the black hole, called the Schwarzschild radius. For a black hole with the mass of our Sun, this radius would be about 3 kilometers. For a supermassive black hole, like the one at the center of our galaxy, which contains about 4 million times the Sun's mass, the event horizon stretches millions of kilometers across. The radius grows linearly, with mass double the mass and you double the radius. Despite these varying sizes, the fundamental nature of the event horizon remains the same. It's the mathematical surface where the escape velocity equals the speed of light. Think about what escape velocity means. On Earth, you need to throw something upward at about 25,000 miles per hour for it to escape the planet's gravity and never fall back down. Get closer to a massive object and the escape velocity increases. At the event horizon of a black hole, the escape velocity reaches 186,282 miles per second. The speed of light. Since nothing can travel faster than light, nothing that crosses the event horizon can ever escape. But here's where things become truly strange. Time itself behaves differently near a black hole's edge. According to Einstein's general relativity, gravity doesn't just bend space, it warps time as well. The stronger the gravity, the slower time passes relative to an observer far away from the gravitational source. Near the event horizon, this time dilation becomes extreme. Picture two observers, one hovering safely far from the black hole, another descending toward the event horizon. The descending observer checks their watch, and everything seems normal to them. Time passes at its usual rate from their perspective. They breathe normally, their heart beats regularly, they think their thoughts at the normal pace. But to the distant observer watching through a powerful telescope, something bizarre is happening. The descending person appears to be moving slower and slower. Their movements become sluggish, their signals take longer and longer to arrive, and as they approach the event horizon, they appear to nearly freeze in place. This isn't an optical illusion or a trick of perception. Time genuinely runs slower in stronger gravitational fields. As the descending observer approaches the event horizon, each second they experience corresponds to longer and longer periods for the distant observer. At the exact moment they cross the event horizon, from the distant observer's perspective, time for them appears to stop completely. They would appear frozen at the edge, never quite crossing over, their image becoming increasingly redshifted and dim, eventually fading from view entirely. But from the perspective of the person crossing the event horizon, nothing special happens at that precise moment. There's no wall, no barrier, no sensation of crossing a threshold. They would pass through the event horizon and continue falling inward, still experiencing time normally from their own reference frame. This is one of the most counterintuitive aspects of black holes. The event horizon is only special to outside observers. To someone crossing it, the moment passes without any local indication that anything significant has occurred. However, there is something that would become increasingly noticeable as you approached and crossed the event horizon: tidal forces. These arise because gravity weakens with distance, and different parts of your body would be at different distances from the black hole's center. If you fell feet first toward the black hole, your feet would experience stronger gravity than your head. This difference in gravitational pull creates a stretching force. For a stellar mass black hole, these tidal forces become extreme well before you reach the event horizon. The difference in gravitational pull between your head and feet would stretch you vertically while simultaneously squeezing you horizontally, a process astrophysicists have termed spaghettification. Long before reaching the event horizon, the tidal forces would overcome the molecular bonds holding your body together, stretching you into a thin stream of atoms. This would be an absolutely fatal experience occurring far from the event horizon itself. For supermassive black holes, the situation is different. Because they're so much larger, the tidal forces at the event horizon are actually quite mild. You could cross the event horizon of a supermassive black hole, and for a while at least, experience no unusual forces at all. The spaghettification would come later, as you continued falling inward toward the singularity where tidal forces eventually become infinite, regardless of the black hole's size. The event horizon is also where the nature of space and time exchange roles, in a sense. Outside the event horizon, you can choose your direction in space. You can go left or right, up or down, toward or away from the black hole. Time, on the other hand, only flows in one direction, forward. But once you cross the event horizon, this changes. Moving inward toward the singularity becomes as inevitable as moving forward in time is outside the black hole. Just as you can't choose to move backward in time in normal space, you can't choose to move away from the singularity once inside the event horizon. All possible paths through space-time, every trajectory you could take, lead inward. Light behaves strangely at the event horizon as well. Just outside the horizon exists a region called the photon sphere, where light can orbit the black hole in unstable circular paths. Photons at exactly this radius, moving in exactly the right direction, will circle the black hole indefinitely. though any tiny perturbation will cause them to either spiral inward or escape outward. If you could somehow position yourself at the photon sphere and look sideways, you might theoretically see the back of your own head as light from you travelled around the black hole and returned. At the event horizon itself, photons can move along the surface, neither escaping nor falling inward, but this is an unstable equilibrium. Any photon aimed even slightly inward will fall toward the singularity. Any photon aimed even fractionally outward will escape to infinity, though heavily redshifted by the time it reaches distant observers. The effects of gravitational redshift become extreme near the event horizon. Light climbing out of a deep gravitational well loses energy, shifting toward longer wavelengths, toward the red end of the spectrum and beyond into infrared and radio waves. A flashlight shining from near the event horizon would appear dimmer and redder to a distant observer. Right at the event horizon, light is redshifted infinitely, meaning the energy of any photon trying to escape becomes zero. This is another way of understanding why nothing can escape. Even light, trying to leave the event horizon, has all its energy drained away by the gravitational field. Black holes can rotate, and rotation adds another layer of complexity to the event horizon. A rotating black hole drags space-time around with it in a process called frame dragging. Close to the black hole, space itself is being pulled around in the direction of rotation. There's a region called the ergosphere outside the event horizon, where this frame dragging is so strong that nothing can remain stationary. Everything must rotate with the black hole, even if it has enough energy to eventually escape. For a rotating black hole, the event horizon is actually smaller than it would be for a non-rotating black hole of the same mass, and it's oblate rather than perfectly spherical, bulging slightly at the equator. At the poles, you could get closer to the singularity before crossing the point of no return than you could at the equator. The material falling into a black hole doesn't simply disappear the moment it crosses the event horizon. Before crossing, matter often forms an accretion disk, a swirling disk of gas, dust, and plasma spiraling inward. Friction in this disk heats the material to tremendous temperatures, often millions of degrees, causing it to radiate intense X-rays and other radiation. This radiation comes from outside the event horizon and can escape, making accreting black holes among the brightest objects in the universe, even though the black hole itself emits nothing. As material in the accretion disk spirals closer to the event horizon, it accelerates to tremendous velocities, often reaching significant fractions of the speed of light. The innermost stable circular orbit, the closest distance where material can orbit without inevitably falling in, lies just outside the event horizon. Material at this radius whips around the black hole in fractions of a second, subjected to intense tidal forces and heated to extreme temperatures before making its final plunge across the event horizon. At the quantum level, something remarkable happens right at the event horizon. Stephen Hawking predicted that quantum effects near the event horizon would cause black holes to emit radiation, now called Hawking radiation. Virtual particle pairs constantly pop into existence throughout space, normally annihilating each other almost immediately. But at the event horizon, one particle of the pair can fall into the black hole, while the other escapes. To a distant observer, the black hole appears to be emitting radiation with a temperature inversely proportional to its mass. For stellar mass black holes, this temperature is incredibly tiny, far colder than the cosmic microwave background, so the effect is purely theoretical at present. But over unimaginably long timescales, Hawking radiation would cause black holes to slowly evaporate. The event horizon represents one of the most profound boundaries in physics, a one-way membrane in space-time itself. It's a place where our intuitions about time, space, and causality break down, where the fabric of reality becomes so warped that the normal rules no longer apply. Everything that crosses this boundary is lost to the outside universe forever, adding to the black hole's mass and slightly expanding its event horizon, while the information about what fell in appears to be lost forever, creating paradoxes that physicists still struggle to resolve. The edge of a black hole is truly an edge, not just of a physical object, but of our ability to observe, to know, and to understand the universe. What alien civilizations might actually look like? When most people imagine alien civilizations, they picture humanoid beings with large heads, sleek bodies, and advanced technology that allows them to cross the vast distances between stars. Science fiction has given us countless variations: green-skinned Martians, insectoid hive minds, crystalline energy beings, peaceful explorers, and hostile invaders alike. But what would alien civilizations actually look like if we base our expectations on biology, physics, chemistry, and evolutionary principles rather than imagination alone? The answer reveals possibilities both familiar and utterly strange, shaped by the same fundamental laws that govern life on Earth, but expressed through the infinite variations that different worlds and evolutionary histories would create. The foundation of any alien civilization begins with evolution. On Earth, every organism exists because its ancestors survived and reproduced more successfully than competitors. Natural selection shaped everything from bacterial flagella to human brains, optimizing organisms for their specific environments and challenges. The same process would operate on any world where life exists. Alien organisms would be shaped by their planet's gravity, atmosphere, temperature, available nutrients, predators, and countless other factors operating over millions or billions of years. Evolution is relentless, creative, and opportunistic, finding solutions to survival challenges through whatever mechanisms work. Gravity would profoundly influence alien body structures. On a high-gravity planet, perhaps 1.5 times Earth's gravity, organisms would need stronger skeletal structures to support their weight. Animals might evolve shorter, stockier bodies with thicker bones and more powerful muscles. Tall, slender forms would be disadvantageous because they would require too much structural support and energy to maintain. Intelligent beings on such a world might stand only 3 or 4 feet tall despite being as massive as humans, with powerful legs and low centers of gravity to move efficiently under the stronger gravitational pull. On a low-gravity planet, the opposite constraints would apply. With less gravitational force to overcome, organisms could grow taller and more delicate. Bones could be lighter and more slender. Flying might be easier, allowing evolution to produce larger flying organisms than Earth's giant pterosaurs. Intelligent beings might stand 8 or 10 feet tall with elongated limbs, moving with a grace that would seem almost balletic to Earth-based observers. Their skeletal structure might resemble bird bones, hollow and reinforced with internal struts rather than solid like mammalian bones. The atmospheric composition would shape how aliens breathe and what biochemistry they use. On Earth, most complex life uses oxygen for metabolism because burning fuel with oxygen releases large amounts of energy efficiently. But oxygen was not always abundant. Early Earth had an atmosphere dominated by nitrogen, carbon dioxide, methane, and other gases. The oxygen we breathe today came from photosynthetic bacteria that gradually transformed the atmosphere over billions of years in what's called the Great Oxidation Event. An alien planet might never undergo such a transformation, leaving its atmosphere oxygen poor. Life there might use different metabolic pathways, perhaps based on sulfur compounds, hydrogen, or methane. The type of star a planet orbits would influence alien vision and perhaps their entire sensory experience of reality. Our sun emits most strongly in visible light wavelengths, the colours we can see, and Earth's organisms evolved eyes sensitive to these wavelengths because that's where the most light was available. but a planet orbiting a red dwarf star would receive most of its light in infrared wavelengths. Organisms evolving there might develop eyes sensitive to infrared rather than visible light. To them, what we call visible light might be invisible ultraviolet, and their daylight would be our infrared. An alien from such a world would perceive colours and see objects in ways completely foreign to human experience. Conversely, a planet orbiting a hotter, bluer star would receive more ultraviolet light. Evolution might produce eyes sensitive to ultraviolet wavelengths, allowing these aliens to see patterns and colours invisible to humans. Many Earth organisms, including bees and some birds, can already see into the ultraviolet range, perceiving patterns on flowers and plumage that humans cannot detect without special cameras. An alien species with full ultraviolet vision would experience a visual world enriched with information and beauty we cannot access. Communication methods would evolve based on environmental constraints and available sensory channels. On Earth, humans primarily communicate through sound, speaking and hearing, supplemented by visual cues like facial expressions and gestures. But sound travels poorly in thin atmospheres and not at all in vacuum. An alien species on a world with a thin atmosphere might rely more heavily on visual communication, colour changes, bioluminescent patterns, or elaborate gestural languages. Octopuses on Earth already use colour-changing skin cells, called chromatophores, to communicate, creating flowing patterns across their bodies. An intelligent species with similar abilities might communicate through rapidly shifting colour displays, conveying complex ideas through patterns that flow across their skin in what would appear to us as living art. Some aliens might communicate through vibrations transmitted through the ground or through their planet's oceans. Whales and elephants on Earth use low-frequency sounds that travel great distances. Elephant calls can travel several miles through the ground. An intelligent species might evolve specialized organs for creating and detecting vibrations, communicating through seismic signals that travel through rock or sediment. Their language would be invisible and inaudible to humans without special equipment to detect the vibrations. Chemical communication, already used extensively by Earth's insects through pheromones, might become the primary communication method for some species. Aliens might communicate through releasing complex mixtures of chemicals that other members of their species detect through sensitive chemoreceptors. Their language would consist of scents and tastes, with grammar and syntax encoded in the ratios and combinations of different molecules. To humans, their most profound poetry and scientific papers would be nothing more than smells. Body structure would reflect evolutionary history and environmental pressures. The bilateral symmetry seen in most Earth animals, a left side mirroring a right side, emerged early in evolution and became locked in. But aliens might evolve radial symmetry like starfish, with body parts arranged around a central axis. An intelligent being with radial symmetry might have arms, eyes, and sensory organs distributed evenly around their body, giving them a 360-degree field of awareness with no natural front or back. Their psychology and culture might be profoundly affected by experiencing the world without a preferred direction of travel or attention. The number of limbs is not fixed by any physical law. Earth's vertebrates settled on 4 limbs relatively early in evolutionary history, but arthropods, insects, spiders, crustaceans have 6, 8, or even dozens of legs. An alien species might evolve with 3 limbs arranged in a triangle, giving them stable tripod support at all times. They might have 6 limbs, 4 for walking and 2 manipulator arms. Or they might have dozens of tentacles like an octopus, each capable of independent complex movement and manipulation. Their tool use and technology would develop along entirely different lines than human technology, shaped by their different manipulative abilities. Intelligence itself might manifest in forms unlike human intelligence, human intelligence is highly centralized. Most of our cognitive processing occurs in our brain, a single organ in our head. But octopuses, among Earth's most intelligent invertebrates, have a distributed nervous system with neurons throughout their arms that can make independent decisions. An alien species might have multiple brain centers distributed throughout their body, or they might have a collective intelligence where individual organisms are relatively simple, but groups display emergent intelligence through their interactions, similar to how ant colonies solve complex problems that individual ants cannot. Social structure would influence civilization development. Humans are intensely social primates who naturally form groups, cooperate, compete, and create complex hierarchies. An intelligent species that evolved from solitary predators might have very different social instincts, perhaps coming together only to mate and raise young, then separating again. Their civilization would be built by individuals who value isolation and independence over community and cooperation. Or aliens might be eusocial, like bees or ants, with specialized castes, workers, soldiers, reproducers, genetically programmed for different roles. Their civilization might function as a superorganism where individual identity barely exists. Lifespan would profoundly affect culture and technology development. If an alien species naturally lives for thousands of years, they might approach problems with a patience humans cannot fathom, willing to spend centuries on single projects. Their sense of urgency and change would operate on timescales that would frustrate any human trying to interact with them. Conversely, a species with lifespans of only a few years might compress their entire cultural and technological development into periods that humans would find incomprehensibly rapid. Environmental factors would shape not just biology, but psychology and culture. A species that evolved in oceans might think about space and boundaries very differently than land-dwelling humans. Without solid ground beneath them, without permanent structures that last for generations, their concepts of property, territory, and permanence might be fluid in ways humans struggle to understand. A species that evolved in dense forests with limited sightlines might have very different concepts of distance and perspective than humans who evolved in open savannas, where seeing for miles was possible and valuable. Technology would develop based on available resources and environmental challenges. A civilization on a water world with no dry land would never discover fire, fundamentally altering their technological development pathway. Without fire, they couldn't easily work metals, make pottery, or develop steam power. Their technology might focus on biological engineering, breeding organisms to serve specific functions, or on working with materials that don't require heat processing. They might develop advanced understanding of hydrodynamics, pressure, and acoustic phenomena, while lacking technologies that humans developed early. A civilization on a planet with extreme temperature swings might prioritize insulation and environmental control. A species on a tidally locked planet with one side in permanent daylight and the other in eternal darkness might build their civilization in the twilight zone between extremes. Or they might develop two separate cultures adapted to the radically different environments. Their technology would need to handle these extremes, perhaps leading to advanced materials science long before other fields developed. Reproduction methods would influence family structures and social organization. If aliens reproduce through spawning like fish, releasing eggs and sperm into water where fertilization occurs externally, they might have no concept of nuclear family or parental bonds. Eggs might be raised communally or even left to develop independently. If reproduction requires 3 or more sexes simultaneously, their social structures and mating rituals would be incomprehensibly complex to humans. If they reproduce through budding or fission, creating genetic copies of themselves, their concepts of individuality and identity might be fundamentally different from species that reproduce sexually and value genetic diversity. Sensory experiences beyond human comprehension might exist. Some Earth organisms detect magnetic fields, electric fields, pressure changes, or polarized light, senses humans lack entirely. An alien species might perceive reality through senses we don't possess and cannot easily imagine. They might see the world through echolocation like bats, building a sonic map of their environment. They might sense electrical fields like sharks detecting the bioelectric signatures of other organisms. They might perceive time differently, with reaction times much faster or slower than humans, making their subjective experience of duration incompatible with ours. The Fermi paradox asks why, if alien civilizations are likely to exist, we haven't detected them yet. One possible answer is that we're looking for the wrong things. We search for radio signals because that's how we communicate, and we look for visible structures, like cities, because that's how we build. But an alien civilization might never develop radio technology, using entirely different communication methods. They might build in ways that leave no visible trace from space. They might exist on entirely different timescales, civilizations that rise and fall in centuries, while humans are still learning to farm, or civilizations that operate so slowly that their entire recorded history spans less time than a human lifetime. If contact ever occurs between human and alien civilizations, the challenges would be immense. Even if both species are trying to communicate, fundamental differences in sensory experience, cognition, timescales, and conceptual frameworks might make mutual understanding nearly impossible. Imagine trying to explain color to someone born blind, or music to someone born deaf, or love to a species that doesn't experience emotions. Now multiply those challenges by every aspect of existence: time, space, causation, identity, purpose. Communication might require generations of effort and specialized translation technologies we haven't yet imagined. What alien civilizations might actually look like encompasses possibilities ranging from vaguely familiar, carbon-based organisms breathing oxygen on Earth-like worlds, shaped by convergent evolution into forms somewhat similar to Earth's creatures, to utterly incomprehensible beings whose very existence challenges our definitions of life, intelligence, and civilization. They might be silicon-based entities living in molten rock at temperatures that would vaporize Earth's organisms. They might be electromagnetic patterns in planetary magnetic fields, or chemical reaction networks in liquid methane seas, or quantum coherence patterns in neutron star crusts. The universe is vast and ancient, and if intelligence has emerged elsewhere, it has had billions of years and countless different environments in which to develop into forms limited only by physics, chemistry, and the creative power of evolution, operating across deep time on worlds we've never seen. What is dark matter, and why can't we see it? Imagine trying to understand a conversation in a crowded room while wearing earplugs. You can see people's mouths moving, see their gestures, watch them react to each other, but you can't hear the words being spoken. You know communication is happening, the evidence is clear in the movements and responses, but the medium of that communication remains completely inaccessible to you. This is somewhat like humanity's relationship with dark matter. We can see its effects throughout the universe, observe how it shapes galaxies and bends light, measure its gravitational influence on everything around it. Yet the substance itself remains invisible and intangible to every instrument we've built to observe the cosmos. Dark matter makes up approximately 85% of all matter in the universe. Let that sink in for a moment. Everything you can see, every star, every galaxy, every glowing nebula, every planet, every atom in your body represents only about 15% of the matter that exists. The rest, the overwhelming majority, is dark matter, and it surrounds us, permeates us, flows through us, yet reveals itself only through its gravitational effects. The story of dark matter's discovery begins not with a sudden revelation, but with decades of observations that didn't quite make sense. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a collection of over 1,000 galaxies bound together by gravity. He measured how fast these galaxies were moving within the cluster and used these velocities to calculate how much mass must be present to keep the cluster gravitationally bound. What he found was shocking. The galaxies were moving so fast that they should have escaped the cluster's gravity and flown apart long ago, unless the cluster contained far more mass than could be seen in the form of stars and gas. Zwicky proposed that some form of dark matter must exist, matter that didn't emit light, but provided the additional gravity needed to hold the cluster together. His idea was largely ignored for decades. It seemed too radical, too strange. Surely there was a simpler explanation. Perhaps astronomers were just missing some normal matter, dust clouds or dim stars that hadn't been detected yet. But the evidence kept accumulating. In the 1970s, astronomer Vera Rubin conducted detailed studies of how stars and gas move within spiral galaxies. According to the laws of gravity and orbital mechanics, objects farther from the center of a galaxy should move more slowly, just as planets farther from the Sun orbit more slowly than those closer in. Mercury races around the Sun in just 88 days, while distant Neptune takes 165 years to complete one orbit. The same principle should apply to galaxies. Stars near the edge should crawl along in their orbits compared to stars closer to the galactic center. But that's not what Rubin found. She observed that stars at the outer edges of galaxies moved just as fast as stars closer to the center, sometimes even faster. The rotation curves of galaxies were flat rather than declining, which could only mean one thing. There was far more mass in these galaxies than could be accounted for by visible stars and gas. And this extra mass wasn't concentrated at the center where most of the visible matter was. It extended far beyond the visible disk, forming a massive spherical halo of invisible matter surrounding each galaxy. Picture a galaxy in your mind, a spiral with graceful arms of stars spinning around a bright central bulge. Now imagine that entire visible structure is embedded within a much larger sphere of dark matter, extending perhaps 10 times farther than the visible stars reach. This dark matter halo contains several times more mass than all the stars, gas and dust combined, yet it emits no light, no radio waves, no X-rays, nothing we can detect directly. The evidence for dark matter extends far beyond galaxy rotation curves. Gravitational lensing provides some of the most compelling proof. According to Einstein's theory of general relativity, mass warps the fabric of spacetime, and light follows the curves in this warped spacetime. When light from a distant galaxy passes near a massive object, its path bends. Just as light bends when passing through a glass lens. The amount of bending depends on how much mass is present. Astronomers observe light from distant galaxies being bent and distorted as it passes through galaxy clusters. By measuring this distortion carefully, they can map out exactly where mass is concentrated in these clusters, creating what's essentially a gravity map. When they do this, they find that most of the mass, about 90%, isn't where the visible galaxies are. It's distributed in a much larger structure, consistent with massive halos of dark matter. One of the most dramatic examples came from studying a structure called the Bullet cluster, where two galaxy clusters had collided and passed through each other. During the collision, the hot gas from each cluster, which is normal matter, slowed down and remained near the collision site, heated by the impact. But the dark matter from each cluster, which doesn't interact with normal matter except through gravity, passed right through and continued moving. By mapping the gravity through gravitational lensing, astronomers could see that most of the mass had separated from the visible gas, providing direct evidence that dark matter and normal matter are distinct substances. So what is dark matter made of? This is one of the deepest mysteries in physics. And the honest answer is that we don't know. We know what it isn't. It's not made of atoms, protons, neutrons, or electrons. It's not any form of normal matter that we're familiar with. We call normal matter baryonic matter, and dark matter is something entirely different, something that exists outside the catalogue of particles that make up everything we can touch and see. The most popular hypothesis is that dark matter consists of particles that simply don't interact with electromagnetic radiation. Light, radio waves, X-rays, any form of light across the entire spectrum. These hypothetical particles, often called WIMPs, weakly interacting massive particles, would have mass and exert gravity, but they wouldn't emit, absorb, or reflect light. They would be essentially transparent to electromagnetic radiation, which is why we can't see them. Imagine a particle that could pass through matter almost as if it weren't there. Billions of these particles might be flowing through your body right now, passing through the Earth, streaming through space, and you would never know. They don't collide with atoms, don't scatter off electrons, don't leave any trace except for their collective gravitational influence. This is what dark matter particles would be like. Ghost particles that fill the universe, but interact with normal matter only through the weakest of forces. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and background radiation, trying to catch the rare interaction of a dark matter particle with normal matter. These detectors contain tanks of specially purified materials, cooled to near absolute zero, instrumented with sensors that can detect the tiniest energy deposit. The idea is that occasionally, very rarely, a dark matter particle might collide with a nucleus in the detector, releasing a tiny amount of energy that could be measured. So far, despite decades of searching with increasingly sensitive experiments, no one has definitively detected a dark matter particle. Another possibility is that dark matter consists of primordial black holes that formed in the early universe, not from collapsing stars, but from density fluctuations shortly after the Big Bang. These would be dark by their very nature, since black holes don't emit light. However, careful observations suggest that primordial black holes can't account for all the dark matter. They would produce observable effects, like gravitational microlensing when they pass in front of distant stars. And we don't see these effects at the level that would be expected if most dark matter were in this form. Some theories propose that dark matter might be axions, extremely light particles that were produced in enormous quantities in the early universe. These would be very different from WIMPs, much lighter, much more numerous, behaving more like a wave than individual particles. Detecting axions requires different experimental approaches, and several experiments are currently searching for these elusive particles. There's even a possibility, though most physicists consider it less likely, that dark matter doesn't exist at all. Instead, perhaps our understanding of gravity is incomplete, and the theory needs to be modified to explain the observations without requiring invisible matter. These modified gravity theories, called MOND, modified Newtonian dynamics, and various relativistic extensions, can explain some observations but struggle with others, like the bullet cluster, which seems to require actual dark matter to explain. Dark matter played a crucial role in the formation of structure in the universe. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny variations in density. These variations were the seeds of all future structure: galaxies, galaxy clusters, and the cosmic web. But normal matter coupled to radiation in the early universe couldn't collapse and clump together efficiently. Dark matter, which didn't interact with radiation, could begin collapsing earlier, forming gravitational wells that normal matter eventually fell into. Without dark matter, Galaxies, as we know them, couldn't have formed in the time available since the Big Bang. Today, dark matter continues to shape the universe. It forms the gravitational scaffolding along which galaxies are distributed. It determines how galaxy clusters form and evolve. It affects how galaxies merge and interact. Every large-scale structure in the universe exists because of dark matter's gravitational influence. On smaller scales, dark matter fills our own galaxy. The Milky Way sits within a dark matter halo that extends far beyond the visible disk of stars. This halo contains perhaps 10 times more mass than all the stars in the galaxy. As our solar system orbits the galactic center, we're moving through this sea of dark matter. At any given moment, thousands of dark matter particles might be passing through every cubic centimeter of space, though detecting even one of them remains beyond our current capabilities. The invisibility of dark matter is not a limitation of our instruments. It's a fundamental property of the substance itself. We can't see it because it doesn't interact with light in any way. We can't build a better telescope or a more sensitive camera to observe it directly. The only way we know it exists is through its gravitational effects on the things we can see. It reveals itself in the motion of stars, the bending of light, the structure of the cosmic web, and the evolution of the universe itself. Dark matter surrounds us, shapes the cosmos, and yet remains one of the deepest mysteries in science, a reminder that the universe is far stranger and more complex than our everyday experience might suggest. The solar wind that flows through space. From the surface of the sun, an invisible river flows outward in all directions, streaming past the planets and extending far beyond the orbit of Pluto into the distant reaches of the solar system. This is the solar wind, a continuous flow of charged particles, primarily electrons and protons, that escape from the sun's outer atmosphere and race through space at speeds ranging from 250 to over 500 miles per second. This wind carries with it pieces of the sun itself, along with magnetic fields that thread through the solar system, creating an enormous bubble of solar influence that shapes the space environment around every planet. The story of the solar wind begins in the sun's corona, the outermost layer of the solar atmosphere that extends millions of miles above the visible surface. The corona is paradoxically much hotter than the surface below it, while the sun's visible surface, the photosphere, has a temperature of about 10,000 degrees Fahrenheit. The corona reaches temperatures exceeding 2 million degrees. This extreme heating, still not completely understood, but likely involving magnetic fields and wave energy, gives particles in the corona so much energy that many of them move faster than the sun's escape velocity. Imagine standing at the sun's surface and throwing a baseball upward. To escape the sun's gravity, you would need to throw it at about 380 miles per second. In the corona, thermal energy heats particles to such extreme temperatures that a significant fraction of them are moving faster than this escape velocity. These particles don't fall back to the sun. They stream away into space, carrying energy and momentum with them. The sun is essentially evaporating, losing mass continuously through this process, though at a rate so slow that it would take trillions of years to evaporate completely. The solar wind is not uniform. It flows faster from some regions of the sun than others, creating a complex structure as it expands outward. Above the sun's equatorial regions, where magnetic field lines tend to loop back to the surface, the solar wind emerges more slowly, typically around 250 miles per second. But at the sun's poles and in coronal holes, regions where magnetic field lines extend far into space, rather than looping back, the wind flows much faster, reaching speeds of 500 miles per second or more. These variations in speed create interaction regions where fast solar wind catches up to slow solar wind. Imagine cars on a highway where fast-moving traffic overtakes slower-moving traffic. The fast solar wind compresses the slow solar wind ahead of it, creating regions of enhanced density and magnetic field strength. These co-rotating interaction regions, named because they rotate with the Sun as it spins, sweep through the solar system like a spiral pattern, buffeting planets with alternating streams of slow and fast wind. As the solar wind flows outward, it carries the Sun's magnetic field with it. The magnetic field lines become stretched and twisted, creating a spiral pattern much like water from a rotating garden sprinkler. This interplanetary magnetic field threads through the entire solar system, connecting magnetically active regions on the Sun to the distant reaches of space. When magnetic field lines from different regions of the Sun come together, in space they can reconnect, releasing energy and accelerating particles to even higher speeds. The solar wind is not just a steady breeze but includes violent gusts and storms. When an eruption occurs on the Sun, a solar flare or a coronal mass ejection, enormous quantities of plasma and magnetic field can be hurled into space far faster than the normal solar wind. A coronal mass ejection can contain billions of tons of material moving at speeds up to several thousand miles per second. When one of these structures reaches Earth, typically 1 to 3 days after leaving the Sun, it can compress Earth's magnetic field, trigger spectacular auroras, and potentially disrupt satellites, power grids, and communication systems. The journey of a solar wind particle from the Sun to Earth takes about 4 to 5 days travelling at typical speeds. During this journey, the particle encounters very little. Space between the Sun and Earth is remarkably empty. A cubic inch of the solar wind near Earth contains only about 5 to 10 protons, far more tenuous than even the best vacuum we can create in laboratories on Earth. Yet despite this extreme sparseness, the solar wind carries significant momentum and energy simply because of the vast volume through which it flows and the speeds at which it travels. When the solar wind encounters a planet, what happens depends on whether that planet has a magnetic field. Earth's magnetic field creates a protective bubble called the magnetosphere that deflects most of the solar wind around the planet. The interaction is dynamic and complex. The leading edge of Earth's magnetosphere, called the bow shock, is where the supersonic solar wind first encounters Earth's magnetic field and slows down abruptly, much like air piling up in front of a supersonic aircraft creates a shock wave. This shock heats the solar wind and diverts it around Earth's magnetosphere, creating a turbulent boundary layer called the magnetosheath. Some solar wind particles do manage to penetrate into Earth's magnetosphere, particularly when reconnection occurs between the interplanetary magnetic field and Earth's magnetic field. These particles get funneled along Earth's magnetic field lines toward the polar regions, where they collide with atoms in the upper atmosphere, creating the shimmering curtains of light we call auroras. The green and red colours come from oxygen atoms at different altitudes being excited by these collisions, while nitrogen produces blue and purple hues. Planets without magnetic fields like Mars and Venus experience the solar wind very differently. Without a protective magnetic bubble, the solar wind interacts directly with the upper atmosphere. Over millions of years, this interaction strips away atmospheric particles, carrying them off into space. Mars, which once had a thicker atmosphere and possibly liquid water on its surface, has lost much of its atmosphere to this process. The solar wind literally peels away the outer layers of the Martian atmosphere, particularly during strong solar storms, gradually transforming Mars from a potentially habitable world to the thin, dry atmosphere we observe today. The Moon, with neither atmosphere nor magnetic field, receives the full force of the solar wind directly on its surface. Solar wind particles impact the lunar regolith, becoming implanted in the soil. Over billions of years, this process has altered the chemistry and appearance of the lunar surface, darkening it and creating what scientists call space weathering. Ancient lunar rocks brought back by Apollo astronauts contain trapped solar wind particles that serve as a record of how the Sun's output has changed over time. Giant planets like Jupiter and Saturn have enormous magnetospheres that extend millions of miles into space. Jupiter's magnetosphere is so large that if we could see it from Earth, it would appear several times larger than the full moon in the sky. The solar wind compresses these magnetospheres on the side facing the Sun and stretches them into long tails on the night side. Within these giant magnetospheres, the interaction between the solar wind, the planet's magnetic field, and particles from the planet's moons creates some of the most intense radiation environments in the solar system. The solar wind doesn't flow forever. Far from the Sun, billions of miles beyond the orbits of the planets, it begins to slow down as it encounters the interstellar medium, the dilute gas and plasma that fills the space between stars. The Voyager spacecraft, launched in 1977, have travelled far enough to cross the boundary where the solar wind slows to subsonic speeds, called the termination shock. This boundary is not spherical, but is pushed outward in the direction the solar system is moving through the galaxy and compressed in the opposite direction. Beyond the termination shock lies a region called the heliosheath, where the solar wind has slowed but still moves outward, compressed and heated by its interaction with the interstellar medium. The exact shape and extent of this region depend on the strength of the solar wind and the pressure of the interstellar medium outside. Voyager 1 and Voyager 2 have now crossed even farther, passing through the heliopause, the outer boundary where the solar wind effectively stops and interstellar space begins. They are now in a region where the dominant flow is no longer from the Sun, but from the galaxy itself. The structure created by the solar wind, this vast bubble of solar influence, extending billions of miles in all directions, is called the heliosphere. It serves as a partial shield, deflecting some of the cosmic rays that stream through the galaxy. Without this protection, the flux of high-energy particles reaching the inner solar system would be higher, potentially affecting planetary atmospheres and creating more radiation hazards for any life on planetary surfaces. The solar wind varies with the Sun's activity cycle. During solar maximum, when the Sun is most active with many sunspots and frequent eruptions, the solar wind is stronger, more variable, and more likely to include fast-moving coronal mass ejections. During solar minimum, when the Sun is quieter, the wind becomes more regular, though still continuous. This 11-year cycle affects space weather throughout the solar system, influencing everything from auroral activity on Earth to the radiation environment encountered by spacecraft. The composition of the solar wind provides a sample of the Sun's outer layers. While predominantly hydrogen, both protons and electrons, the wind also contains helium, making up about 4% of the particles, along with trace amounts of heavier elements, like carbon, nitrogen, oxygen, neon, magnesium, silicon, and iron. These heavier elements are present in much smaller quantities but provide valuable information about solar composition and the processes occurring in the corona. Different types of solar wind have different characteristics. The slow solar wind is denser and cooler, while the fast wind is more tenuous but carries more kinetic energy due to its higher speed. Transient events like coronal mass ejections create temporary structures in the solar wind with dramatically enhanced density, speed, and magnetic field strength. These variations create a constantly changing space environment that spacecraft and planets must navigate. The solar wind also carries information outward from the Sun. Disturbances created by solar activity propagate through the solar wind, and by observing how these disturbances evolve and interact as they move through space, scientists can learn about the properties of the wind itself and the magnetic fields threading through it. Spacecraft throughout the solar system serve as sentinels, measuring the solar wind's properties at different locations and providing a three-dimensional view of how this invisible river flows through our cosmic neighbourhood. Every star produces a stellar wind, analogous to our solar wind, and these winds play important roles in stellar evolution and in shaping the environments around other planetary systems. Hot, massive stars produce fierce stellar winds that can carry away significant fractions of the star's mass over its lifetime. Cool, evolved stars like red giants produce slower but denser winds. Understanding our own solar wind provides insights into these stellar winds throughout the galaxy, connecting the processes occurring in our immediate space environment to the broader evolution of stars and planetary systems across the universe.